And thank you very much to all of you for sharing with me this very interesting topic. Also, thanks a lot for the invitation. So let me just push play and show you a little bit of what's going on here. First and foremost, there's a little bit of previous advertisement. Lo and behold, this over there is my PhD supervisor, Andrew Frolov. And circa 2016, he gave a talk at CITA. Over there at that time and at those space-time coordinates, there was no pandemic condition going on. And this was, you could all see more or less lively what the situation was going on. So this talk is a little bit of a continuation of what happened with the whole technique of trying to, over there, what he tried to expose was more or less the machinery of what was going on when one tries to compute two-point functions and power spectrum for primordial power spectrum of fluctuations. Over there, you have the YouTube link if you're interested. I will go over the details about not only about what happened in that talk, but also what's been going on, what's been improved since then. Let me first give you a first snapshot of more or less what were the initial motivations to address the problem of trying to separate fast and slow timescales in two-point functions. First and foremost, the most interesting and nice results that we got quite a while ago about primordial universe being mainly dominated by fluctuations which are very small and which have approximately Gaussian statistics was quite of a shocking thing. The look for more structure and the look for significant deviations from just perfect Gaussian behavior have been, I would say, at a strategic point to try to connect what we understand in astrophysical and cosmological scales to high energy physics and primary models of evolution for the early universe. As I was telling you, the main point of information here came from the early stages of CMB when people got pretty much shocked by seeing this more or less green screen if you're kind of blind. And the next question that arrived there many years ago is what happened to all the power at low L coming from fluctuations. What could have happened? Well, if we would use just basic Friedmann-Robertson-Walker cosmology, in which space-time essentially is flat Friedmann-Robertson-Walker is just flat space-time, which expands uniformly. And we try to characterize a fluid that drives the expansion. We found out that if we allow that fluid is made out of either standard electromagnetic radiation, which could be ultra-relativistic, sub-relativistic, and any form of matter that we more or less are used to, what we find is that there's not much of a chance for low K modes to escape out of the horizon simply because sound horizon for radiation-dominated or matter-dominated universe is quite far off. So in principle, it was very weird and very shocking to have results such those. And in the absence of reasonable answers, one can pose several alternatives. The one that is, I would say, the paradigm that works better and is mainly accepted by people is the idea that what happens if we can send t to minus infinity and allow the sound horizon to remain more or less flat, so such that low K modes have the chance to escape and then re-enter the horizon much later on. That over there, my friends, is more or less what dominates the paradigm of inflation, which is the second panel that you have on the right. It more or less represents what happens in the evolution story of those K modes. Those are able to escape and then re-enter much later on. The other option is, one other option is to have superluminal fluctuations, which can freely escape and having a varying speed of light theory. This is going to from the point of view of classical mechanics and equations of motion, nothing stops Cherenkov radiation to just escape in normal fluid mechanics. The problem is if we want to think that there is a UV limit in which a theory can be completed. The problem is that quantum fluctuations over there show that these modes propagating with speeds of sound greater than the speed of light have negative dispersion relations, have negative, cross sections. So that is problematic along many other problems that appear in the quantum extension of a potentially theory of, or I would say, an extension that tries to cover standard model and beyond. The third idea that I want to suggest here, along with inflation, is the idea of trying to force causal contact by introducing a balancing phase. It's apparently this is an interesting idea. Why? Because there's no apparently there's no need of energy singularities. It is very complicated. There are no natural mechanisms for a bounce. Even try to create simple like throws when one can, where geodesics can compress and then re-expand, is extremely complicated without having a reservoir of energy in the middle that allows a bunch of curves to contract to a point and then to re-expand. That is logistically very complicated, but in the presence of diverse forms of fluid mechanics, let me put it like this: if you have a non-Newtonian fluid and you just compress it, like this type of oobleck-like fluids, and you compress it to a minimal size, there's going to be a point in which if you continue perturbing the system is going to try to re-expand back up to some natural threshold that it has. So more or less the idea of having imperfect fluids in which non-linear dynamics dominates, it was a potentially nice idea to have. So let me more or less try to wrap up these ideas and try to see what is the thing that one is able to do once that one tries to wrap up this concept with a little bit of equations. First and foremost, since we're talking about a universe that in the background is pretty much homogeneous and fluctuations are fairly small, it is very clear that there's a need to actually talk about the background. In the case of inflation, let's say just standard scalar field model of inflation, single field, is governed by at the background level by simply just these very nice harmonic oscillator equations with potential gradient. We have Friedman equations. In principle, inflation tells us it's a very nice thing because it contains this very nice story of that can in principle contain different configurations of scalar fields with different velocities and different field configurations, and these seem to converge to an attractor and then expand. So inflation was proposed at its very beginning as a very generic stage in which essentially the only thing that one needed to do is to just release an initial condition and it would converge to an attractor and then expand. So it's something more or less interesting to happen. And then what happens is, okay, this is nice for the background, but what about the fluctuations? Well, the fluctuations is about what we want to see in the CMB. Fluctuations come from mainly in such an early stage of the universe, come from tensor fluctuations and scalar fluctuations at the linearized level with second-order equations of motion. The equations of motion are going to look pretty much the same as just a harmonic oscillator with time-dependent frequency as the second equation that I have in there. And then in principle, the important thing would be to try to solve the mode functions to actually see what is the expected amplitude of fluctuations that we can expect from both on scalars and tensor fluctuations, and then compare and try to contrast with what we know and see from Planck and recent missions. Okay, here comes an interesting and simple problem that I want to revisit with you. So I want you to look at the second equation over there, this very nice equation that it tells you second derivative with respect to eta squared of psi. Psi characterizes the size of the fluctuations of our system. Omega squared is a time-dependent frequency. And the idea is in which elegant and more or less simple way we can actually just solve that equation to extract the information from just the amplitude of psi and not the information that comes from the phases. Why do I only care about the information from the amplitude and not from the phases? Because primordial power spectrum for both scalar and tensor curvatures mainly depends in the square of the amplitude of those solutions. Only depends in the squared amplitude of those solutions. Therefore, if we can just evolve simply the envelope of a degree of freedom that oscillates and just tell you what is going to be the amplitude when horizon, at the point of horizon freezing, that would be great. Because in principle, that would make, that would actually solve the problem in let's say, much larger time steps without the need to do approximations about how large or how small omega has to be, what is going to be its specific time dependence. And to do that, I want to present to you a small trick. And I think it's something that's been seen before. You can take that degree of freedom, psi, and write it as L, the amplitude, times e to the I theta k. Okay? If we do the exercise and try to find equations of motion for L and theta, equations of motion for L just simply come from taking the real part of the replacement that I suggest there in the yellow box over there, and the equations of motion for theta come from the imaginary part. The solution to the equations of motion from the imaginary part is quite simple, in fact. It's just, you can simply notice that it's pretty much a first-order equation in which the only information that you need to extract is about the derivatives of the phase degree of freedom in there. So if you replace the solution for what theta prime is in the first equation, you're going to have something that looks like the equation for L double dot K plus omega squared minus omega squared effective at eta naught, L to the fourth over L to the fourth, Lk equals to 0. Interesting thing about that equation, when eta is equal to eta naught, the effective frequency of that system is exactly 0. Therefore, if one happens to have a system in which it is possible to cancel the effective frequency where the oscillator frequency of the system is the highest, one can effectively reduce, maybe not reduce, but shorten a lot the time that one has to wait to solve the full mode equation. And that's more or less what the spirit of what I want to try to convey to you in this talk, is that it is under certain conditions, it is perfectly possible to take these second order differential equations and get rid of the phases and just calculate amplitudes. This is not always possible, but in many cases that we explore, at the very least in the early universe, in the presence of some specific initial conditions, it is entirely possible to have a system in which one has suppressed the oscillation frequencies by a lot. That equation over there, as I've written, was sufficient to actually try to constrain certain models. It's, let's say, Scalarology at its maximum has flourished in amazing ways. One of these, let's say, models that people are trying to use and try to compute and get parameters is essentially, as I'm telling you, inflation is mainly driven by a potential. And there is this very interesting model that we explored at some point called constant roll inflation, in which inflation is just instead of using slow roll conditions, in which one assumed that information about second derivatives and second time derivatives and derivative squared of the field was very small, slow roll approximation was essentially relaxed in this type of models. So instead of using slow roll approximations to calculate observable parameters such as NS and R, which are the scalar tilt and the tensor to scalar ratio, we just solve directly equations of motion in very large numbers and pretty much could fully reproduce the full parameter space for these constant roll models of inflation, which led us to very nice constraints just by solving a simple differential equation proposed more than 140 years ago. So that's interesting. Doing separation for single field models of inflation, it's a nice idea. Let's see what else can be done. So if you start to figure out, well, I have a very good friend that likes a lot high energy physics, and he tells me that there is absolute nonsense to believe that something like inflation with only 1 degree of freedom is supposed to be something that I can call fundamental from the theory. People do believe that there are plenty of degrees of freedom, symmetry breaking happening all over the place, very complicated models with many degrees of freedom involved. Then how can I extend all that knowledge to theories in which inflation is driven by more than one scalar field? It turns out that the technique that I told you about, try to separate amplitude from phase, is actually applicable also for multi-field models of inflation. To do that, instead of being so straightforward about separating xi as L times e to the I theta, let's just say that instead of saying that xi is containing this amplitude and phase, let's assume that one has a vector of phases which rotates in field space, and one has a matrix which contains all the information about the amplitude of the field. Therefore, something like the power spectrum for an n-field model is going to be a symmetric matrix. Why is that? Because you're taking the fluctuations of the, if you want, of the field 1 with the field 2. So you have delta phi 1, delta phi 1, delta phi 1, delta phi 2, delta phi 2, delta phi 1, delta phi 2, delta phi 2. And that over there contains all the information that you need about correlations between primordial fluctuations. That matrix, as you can guess, is symmetric because the correlation of field 1 and the correlation with field 2 is exactly the same as the correlation of field 2 with field 1. So, okay, if the correlation matrix is symmetric, what happens? Are there any clever ways to decompose it into 2 factors such that one of those factors contain all the information I need from the amplitude? And the answer is yes. One way to do it is, let's diagonalize it, and let's take the matrix, eigenvalue, let's say rotation, and try to calculate rotations all over the place. That is a little bit cumbersome because you have to trace all the rotation for an n-dimensional space. In general, for if you believe, I don't know, I really want to appeal to your knowledge about trying to build matrices and rotation matrices in n dimensions. It turns out that for SO2n, that is possible. For SO2n plus 1, that's different. So therefore, there is not a clean structure that allows us to generalize rotation matrices for SO2n plus 1 to be separated and give you very nice clean consistency all relations all the way. But there's another way that is very interesting, and is that when the correlation matrix is positive definite, it turns out that it is always possible to separate that matrix into 2 triangular matrices. One lower triangular, one upper triangular, those two would be, that decomposition is called Cholesky decomposition. People that love image processing, which was the case of my supervisor, love this Cholesky decomposition. Why? Many reasons. First, it involves way less degrees of freedom, so transporting those matrices to reconstruct symmetric matrices later on is much cheaper, and matrices will remain being symmetric. You don't have to calculate all the elements separately, and therefore you just multiply L by L transpose, and boop, you have your symmetric matrix done. But saying something like, okay, I have this multiplet of fields, which I can write as a matrix which contains all the information that I need about amplitudes times a vector that only does this and rotates. I want that vector that rotates to always have unit variance, such that when I take correlation between phi A and phi B, I take LAB, chi, LAB, chi, L and L go out, and I have chi-chi correlation. Chi-chi correlation, I want it to be 1 at all times. If I want correlations of a rotating vector to remain 1 at all times, what do I need to prove? I need to prove that the derivative of that correlator is 0, and that the second derivative of that correlator is 0. If I do that, I obtain very nice consistency relations and even an equation of motion for what L is going to be at every instant of time. Therefore, I can go and use that equation of motion for L and actually reconstruct power spectrum with cross correlations. There is a second thing. When you take second derivatives of something like chi-chi, every time that you take a derivative, you're symmetrizing an operation. For example, you have chi-A, chi-B, you take the derivative, chi.A, chi-B, plus chi-A, chi.B. That over there is a symmetrization between A and B indices. So that's an interesting thing, because if every time that you take derivatives, you end up symmetrizing things, it is perfectly possible that the thing that you're symmetrizing inside, you can add an antisymmetric matrix inside, and the condition that symmetrizes those things looks exactly the same. That small statement over there helps a lot to make the matrices L that contain information of the amplitude to always remain upper or lower triangular. Therefore, it is perfectly possible to use a system of equations to solve for L. And there's been results about that, which are very interesting. One can compute power spectrum of different models. We did that in a nice paper. And okay, apparently from what I've been telling you so far, it is perfectly possible to separate these L's with chi, but does it represent really an improvement in the performance of something that computes power spectrum? And the answer is yes. In the presence of Bunch-Davies vacuum initial conditions, you can see that instead of having a net oscillation frequency for all the matrix element to be more or less like that red line, the oscillation frequency behaves like the blue line. So at the point in which you have the maximal range of oscillation of oscillating scale, the value of omega squared of the rotation of, let's say, the effective rotation frequency squared drops by 3 orders of magnitude. And that means that every mode can be pumped up by something like a factor of, let's say, a time step of a factor of 50 larger, 60 larger. So in the time that you need to calculate one power spectrum, you can build like 50 or 60 of them. So yes, apparently it works. So the idea is, okay, now we have this technology, what we can do with it? Well, it was very nice to come here to CITA because I found this very nice group that Dick has, in which there is Thomas Morrison and Jonathan, who very kindly introduced me at the beginning of this talk. And they are very interested in working in potentials that have more than one field, and that show very interesting features as the entertaining possibility of having dynamic phase transition in the potential. The potential, roughly speaking, looks like this. You have, let's say, a quartic potential in one direction, and then all of a sudden, as time goes by, whoop, the symmetry breaking occurs, and then it returns, and then it occurs, and then it returns. Of course, Jonathan, Tom, and Dick are extremely smart and can do this fully non-linearly, but let's say peewee people like me entertain ourselves with first-order equations of motion, and it's a nice exercise to do first-order perturbative approach and actually try to see what would be the effect of those successive symmetry breakings in the potential when you have more than one of those, which in principle, when you have spontaneous symmetry breaking happening along the potential, I invite you not to see it as dramatically as I want to put it in that picture. Let's just think of it as a small defect that appears in an inflationary potential. If an effect just pops up and let's say the mean field, instead of rolling just transversally over the place, gets a fluctuation, then you care about what actually dynamically happens to that field. Is it able to fluctuate? How is it going to convert energy from one degree to another? Are there going to be isocurvature mode creation? Those things you actually care about. So therefore, trying to produce, let's say, simple potentials in which things just happens to be a good business in order to see the stability of certain predictions. And I want to also, if I'm able to convince you somehow that these are interesting explorations to do, maybe it will be interesting for all of us to try to think about what might happen if, let's say, this can give us some extra reach about what fundamental physics looks as the effects start to occur in standard inflationary potentials. And the story goes a little bit beyond what the textbook tells us about inflation. Okay, so I'm going to talk about the other alternative that I've been talking to you about, which is trying to compute power spectra from inflationary models. More or less recently, there was this very interesting paper by Anna Ijas and Paul Steinhardt saying that there's a possibility of reproducing a bouncing cosmology without introducing singularities or infinite energy points in the middle of the expansion history of the system by considering a nonlinear action. In this case, that nonlinear action represents the action for an imperfect fluid. In this case, I'm going to talk to you about the example of a cubic Galilean. And the interesting thing that Paul Steinhardt and Anna Ilias did was very interesting because they actually used as input the expansion history that they wanted to represent, and from there they derived the features of the theory that they wanted to explore. When we actually try to do that, many interesting things happen. First and foremost, after we try to do parameter reconstructions of what those kind of theories look like, we found out that that things are fairly inescapable in terms of having superluminal propagation of degrees of freedom. Second, ghosts and the possibility of not having stable FRW background stories are not that far from the system. These are multi-valued surfaces, so things just at the background level do not look as happy as one might expect. Furthermore, since I have this very nice code that computes fluctuations and work, yes, up to some fair extent, it's very reasonable to see what happens with primordial fluctuations of CITA. And I really want to invite you to see this plot because, okay, this is not k cubed times amplitude, this is k times amplitude. So I'm talking you about, so I'm telling you that these are all a bunch of blue spectra. And what is interesting is that throughout the bounce, if one changes the instant of time in which one records what happens with amplitude of fluctuations, it turns out that there is an exchange in power between scalar and tensor fluctuations. There is a point in time in which you start producing way more tensor than scalars in a bouncing history. And that's fine. That's a very interesting story that this shows. I would not say that is the most that is the happiest expansion history to ever present, but that's what they're showing. The other thing that happens, and let me go, is that, okay, when I actually try to see what happens with what is the story of evolution of the K modes inside the box, I want to draw a very nice parallel that what happens with fluctuations in the bouncing perspective is something very similar to what happens when one goes to Las Vegas. Whatever happens in Las Vegas stays in Las Vegas. Whatever happens inside the sound horizon of the system stays inside the sound horizon of the system. And that's a very interesting feature that these models have. I want to show you very briefly what are the prospective ideas of work that one can follow when one has a technique that separates amplitudes and phases in a more or less efficient way. First and foremost, one can do fast parameter estimations without doing any slow roll approximations. Consistency relations for R, which is the scalar to the tensor to scalar ratio, and for NS are not necessary anymore. The only thing that one needs to do is to solve perturbations equations directly, and that happens to not be expensive at all. The other thing that it's important that I need to warn you about and is that this formalism that I've been showing you here is not fully crafted and prepared to go to full phase space analysis. If one wants to compute full dynamics of the Wigner ellipse, of how things look when you have pi and phi fluctuations, and you try to work with squeeze states, things are going to look quite funny, because something like a squeeze state breaks this very nice phase cancellation that these models, that this system have. So it would be great to try to, I'm really actually trying to work to extend this technique to actually work and consider something that is not as happy as Bunch-Davies vacuum, which in phase space is just a very nice sphere. Then the other thing that would be interesting to explore is, okay, let's try to also explore what the history is beyond inflation, and let's try to see if other alternatives to inflation can produce up to some fair extent something more or less consistent with what observations show. This is more wishful thinking than actual reality, but it really deserves a shot to actually explore what these dynamical effects might be. What are all of these proposals? Inflation has more than 40 to 50 years old, and as you might know, when you allow certain theoretical idea to grow, alternatives and perspectives and theory starts to produce way and more and more and more and more possible scenarios in which things can happen, and it is prudent to start to constrain some of those. So I'm on the boat of not discarding anything, and let's just try to crank up the numbers and see if things are realistic or not. I want to make emphasis on the second statement that I made there about try to study squeeze states and study things beyond just the simple Bunch-Davies vacuum. And there is an ongoing interest in trying to see primordial power spectrum with features. That interest starts from people that wants to look at primordial black hole formation. And very explicitly, as you can see in the second title, people are actually asking questions about what squeeze states, what initial conditions do in the formation of such states, and what do they do to the power spectrum. Are these things imaginable? Are these things craftable? Are the squeezing parameters something that we can use as priors for observations? Well, those are good questions to make. And if one can have something that efficiently computes these things and creates and suits well to the priors imposed, then why not? again, people from the more fundamental side of things are going to argue that, okay, inflation, it better have some room to something that has more than one field, even if the properties of the other fields are somewhat constrained. So I would always encourage to not disregard what happens with those kind of models. So far, ladies and gentlemen, this is all what I have to say to you. Thank you very much for your attention. And please, I'm looking forward to hear your questions.
Okay, thank you, Tomas. I guess we can give you a virtual hand to start with. Does anyone have any questions? Just go ahead and speak up if you do. Okay, I have a quick question.
Okay.
With the bouncing cosmology,
Mm-hmm.
Can you remind me what the standard prediction is for the gravitational wave spectrum?
In principle, not the prediction, but the statement is that bouncing scenarios are supposed to leave completely unaltered whatever features you build from initial conditions onwards. And most of what these people try to make from starters is to just keep that hierarchy of scalar and tensor fluctuations through the bounds without much of a problem. And what we're seeing is that that's not happening. So yeah, things like clearly the changing sign of H does something to the production of, to the relative ratio of production of scalars versus tensors. And there's something going on there. The other thing is that in principle, the state of the art for bouncing cosmologies is that after the bounce, there's something like an ekpyrotic phase, which actually just cleans up all the spectrum and allows you to have scaling invariant power spectrum. But the reality is that something like an ekpyrotic phase has to be crafted in an extremely careful way because the bounce is something that is very easy to be perturbed. So one of the things that I also wanted to pose here as an alternative is there is another motivation to actually explore squeeze states, and is that there is nothing really carved in stone about what are the initial conditions for a system. And it is very possible that in the case of these bouncing histories, initial conditions and the initial fluid looks like completely erratic and looks like something extremely crazy. And in that case, taking a scaling invariant power spectrum and try to find out and try to do something like inverse scattering problem to find out how the initial states look like is something reasonable to say, to see more or less, okay, what is the status of the form of matter that creates these fluctuations, and what is, if there's something like a quantum state that can represent them, what is going on with that? So this situation, yes, it is true that there are claims about what other things are supposed to happen through the bounds, but instead of just shutting doors and saying, no, this cannot happen, I would try to explore what are the possibilities that the fluids and what are the possibilities that the system offer, given that such and such paradigm accomplishes obtaining a scaling invariant power spectrum. So with this technology, I do suspect that it's perfectly possible to reverse the question and actually asking, what is this substance? What does it do? What is the way the squeeze states look like? And I suspect that that's something that can be in principle asked, instead of just saying, okay, bounds does not exist.
Okay. Anyone else have questions? Okay, I could ask another obvious one. So once you have the 2 points, you might want to break this into an adiabatic and an isocurvature mode, or many isocurvature modes, depending on how many fields you have. Is
Yes,
that projection fairly straightforward as long as you have the backgrounds and probably some integral along the background.
The claim is that the adiabatic mode generates an orthogonal space, but the exact decomposition of what are the perpendicular direction to that adiabatic mode are, it's not really clear. So yes, I suspect that some extra consistency integral is needed to figure out exactly what the adiabatic modes are. Well, yeah, the curvature modes are, sorry.
Okay, but in principle, all that information is there.
In principle, the information should be there, yes.
Okay. Any final questions?
Please go ahead, ask. From the very beginning, something was not clear. I'm more than happy to repeat if needed.
I have a question. You had a phase space plot for the bouncing cosmology that showed about 1 million different regions.
Yes, that was awful, yes.
Can you explain this in some more detail? What is going on here?
Perfect. Okay, so what happens is the following. First, let me explain you more or less what happened here, what allowed us to build such a thing. We used information about h of t and epsilon of t, or sorry, of omega of t as functions. And the statement that Steinhardt and E just did is that using that information, you can tell exactly what the theory looks like. What is the strength of the coupling constants, and what are the kinetic terms that appear in the theory. So therefore, reversing that information, we've found out the equations of motion for phi and phi dot, and using Friedman equations to find out what c squared as a function of phi and phi dot are, and the two Friedman equations, we were able to reconstruct what are, let's say, what are the features and what are the different regions that appear in that field space. For example, that yellow region that you see over there that says no FRW background shows that H regions in which H squared is less than 0. So therefore, there's no expansion history. Then, since the speed of sound square also depends on the fields, and the fields and the field derivatives, we also extracted what were the places in phase space in which the sound speed was greater than 1. And what this phase space map is telling you is that it's not only that, okay, it says many things. First and foremost, the expansion history that Steinhardt and Ijas tried to suggest to generate the bouncing cosmology, instead of having this very nice attracting feature that you can see in inflation in which things converge to an attractor, okay, that over there, the expansion history that they provide is actually a separatrix in phase space. So fields want to be away from that thing, okay? That's one thing. The other thing that happens is that, okay, if you do continuous deformations to the theory, the background, like the bouncing trajectory that you have over there is always going to be extremely close to regions in which the speed of sound of fluctuations is greater than 1. So the paper that we produced is called Unbraiding the Bounds and Superluminality Around the Corner. And this is actually what is going on. If you do a continuous deformation of the theory, the bouncing trajectory is always going to be very, very close to regions where the speed of sound is greater than 1. The other that happens is that there are regions in which that are even closer to the bouncing trajectories in which the speed of sound square is negative, in which h is equal to 0. So yeah, it looks very pathological, and it is actually very pathological. So yeah, this phase space reveals that unfortunately the nonlinear bounds as predicted is not a very reliable expansion. Does not produce a very reliable expansion history with small fluctuations. I would say even small fluctuations really tear apart this picture in a very bad way.
Thanks.
Mm-hmm.
Okay, there's a simple question in the chat. What are PBHs?
Oh, primordial black holes. Yes, generating primordial black holes and gravitational waves. So yeah,
can you expand on that a little bit?
Yes, here's the thing that it's very. This is why I feel that I'm really in the right group to actually talk this situation. The hypothesis is that if one achieves very large values of curvature fluctuations, what you're actually producing is very deep potential wells. If potential gravitational wells are sufficiently deep, then gravitational interaction could be sufficiently strong to pull matter and create a black hole right after the end of inflation. What is very interesting is that most of the claims about producing these features also show that perturbative treatment of curvature fluctuations is completely ruled out. They do have very large, like extremely large values of curvature. And the reality is that when one really wants to approach the problem of actually forming primordial black holes, you really need full GR in order to actually see if something like that can be formed. It is not sufficient to say that an instability can form. And the reason for that is because since gauge is not under control at first order perturbations, you can have free modes that just represent coordinate rotations and coordinate transformation all over the place that give you false large values of curvature. And if that's the case, you're giving a wrong detection showing that there could be a primordial black hole being formed there. So it is like the way which is being trying to be presented is, okay, there is potential possibility for instability in which primordial curvature values can be large, but that on itself is not really an indication that primordial black holes are actually going to form. In order to do that, you need to solve the full nonlinear code. This is only an indication that zeta curvature R, Richie, can be very large, but not more than that. You can have very large R, but no black hole being formed. It's like the formation of black holes also depends on the dynamics of the system. And as far as I know, the dynamics of general relativity is nonlinear. So linearized theories are kind of, so linearized schemes can produce interesting stuff, but are fairly limited. So yeah, it's very nice to make statements about that, but it's not a complete history.
Okay, anyone else? All right, if not, let's thank Tomas one last time. And again, he's set aside some time on Monday if you'd like to have a Zoom chat with him. The link was sent out in the emails earlier. All right, so thanks for coming, everyone. Have a good rest of the week.
Enjoy. See you tomorrow. Bye-bye.